Hi everybody, I'm Sara de Nigris, and what I'll be talking about today are anomalous diffusion processes on networks. And at the end, I will conclude with an application of such regimes in the context of machine learning. So, diffusion processes, you might have heard in Professor Masuda lectures, that basically they are heavily impacted by network structure. So, in a general setting, a lattice, you would have, for instance, the same probability of hopping on the right or on the left. But then when you have a walker that goes around some graph structure, well, the whole process becomes more complex. So one of the most basic master equation you would encounter is something like this, in which you have that the probability distribution, its evolution, depends heavily on the graph structure through the Laplace operator, which is defined as the adjacency matrix here, the weighted adjacency matrix, and here you have the diagonal matrix, and where the entries are the degrees of the nodes. So such diffusion processes are, of course, more complex due to the network structure, but when you are in a network, you can basically exploit them to develop algorithms that are extremely powerful for searching, for classification, and also for clustering, as it was also already mentioned in Professor Masuda lectures. So in this specific lecture, we will look at some specific regimes, which are called anomalous diffusion, and we'll see a couple of practical results that describe those regimes. So first, anomalous diffusion is defined basically on continuous media and lattices through the variance behavior. So in normal diffusion, you would have that this variance scales as the time. So alpha here, the exponent will be 1. But when you encounter some anomalous diffusion, well, you might have that this alpha exponent is different from 1. So you might ignite the different regimes through changing the Walker behavior. So for instance, you can have a subdiffusion regime, and in this case, you might need to use waiting time PDF, and in this case, you would like to have a divergent mean, so a divergent first moment. So what are you saying is that your walkers are allowed to have long waiting times. On the other hand, if you would like to have a super diffuser regime, what you would need at a local level is a jump PDF. We will see later what is exactly. But in this case, you would need this PDF to have a divergent second moment. So basically, what you are implying is that your walker is able to make long jumps, very long jumps that are called the flights. So this is the general picture, very roughly. Let's have a more precise take on it. So, as I said, super diffusion, so to speak, a faster explorational space in which you have this alpha exponent here bigger than 1. So how do you do it? You allow your walker to perform long jumps, and the way it was defined on continuous media was taking a probability distribution for the jump length, where the jump length is here, L, and this probability distribution has a tail, and it is in a power law shape with this gamma exponent here. So basically what you're saying is that the probability of making a long jump is rather big, so that you have a walker that explores very fast the space. But defining this probability distribution implies that you have a metric space, because you have to basically measure this length of the jump. Therefore, when researchers tried to shift to networks, they had basically an intrinsic problem due to this definition. And they have come up with different recipes. One is to redefine the transition probabilities. So you have your transition matrix here, and you say that the probability to jump from I to j is proportional to the geodesic distance from node I to j to some power here gamma. So it was like a very similar to the continuous media version. Or you can take the operator, the fractional, the Laplacian, and you can define a new object which is called fractional Laplacian, in which you put the eigenvalues here. Lambda is the diagonal matrix whose entries are the eigenvalues, and you put it to some gamma power. So two different takes, but what happens is that for every one of them, you have two very expensive steps. One is to have all the path lengths of your networks, which would be the first recipe. The other one would be to diagonalize your Laplacian. So you might have another approach to define super diffusive regimes. And in this case, we try to have a different perspective. So modify, again, the Walker behavior. So in this case, instead of a jump length distribution, we defined a microscopic cascade distribution. So what I mean is that if, in a general case, at each step, either you go left or you go right with some probability, in that case, at every step you choose a little n here number of steps, drawn through this probability that has also a power law tail with a gamma exponent. And therefore, if you start here and you toss a coin and this n, little n here gives you 6, then you perform a cascade of 6 little steps that bring you from your starting point here towards this point here. So at every time step you have the possibility of performing a cascade whose length is decided by this probability distribution of the cascade length. So in this case, with this definition, you are able to come up with a whole calculation of the probability distribution in 1D, so on a line. And what you would obtain is that the probability distribution here of moving at the distance d after k steps, it is actually exhibiting a super diffusive-like regime. Why? Well, because it is, first thing we notice is that it is a self-similar object which depends on this gamma exponent here, exactly as you would expect as from a super diffusive PDF. And also, if you collapse the probability distribution at different times, here k, the variable k is dependent on time because it's the number of steps, you see that they collapse here because of the set similarity, and they show here the factails having thus a Levy shape. So in 1D, it was possible through a microscopic rule that doesn't know a priori the whole topology of the graph to infer another definition of super diffusive regime. The problem here would be that the calculation for more general structures than 1D are very complex, so it's still like an open problem. But you might also have another point of view on super diffusive, on diffusive regimes, and have the opposite perspective, which will be subdiffusive regimes. So again, in lattices and continuous media, it is well known that changing the patterns of activity, you can create subdiffusive regimes in which the variance here of the displacement is sublinear in time because this alpha exponent is smaller than 1. So to ignite those regimes, now you are endowing your walkers with a different property, and this property would be that they can wait. So you define a PDF here, a waiting time PDF, that it also possesses a tail in a power law shape, and this beta exponent here is the one that tunes this waiting time behavior. So also in this regime on networks, it is easy to derive a generalized master equation, and at the end of the calculation, you come up with a probability distribution for your walkers that it has this shape. Basically, you have two ingredients in this formula. One is the time dependence here with the beta exponent, and the other part is the graph dependent part here, because the lambda are the graph eigenvalues. So what is interesting in this calculation is that when you blend the graph structure and the temporal behavior through this waiting time PDF, you obtain that the time dependence is outside the graph dependent term, and therefore all the graph impact in the PDF is basically independent from the time behavior. So what I just said, basically you can see it here. You have 4 networks. This is the probability distribution with respect to time. And these 4 networks have different spectral gaps that is shown here. So basically there are 2 modules that I connect more, so they become from one graph to the other, they become more connected. But the problem is that since the walkers can wait with some beta exponent here, basically you have the same behavior. So this is like the slope, it's the same, so it depends on the beta exponent for all the graphs. So basically the probability distribution has become blind to the graph structure. And this result is basically given by the interplay between the dynamics and the graph structure itself. So the conjunction of the two, the dynamical aspect and the graph aspect, is something that is very useful in machine learning. So in machine learning, you might want to use diffusion processes to, for instance, perform classification tasks. So there is of course, machine learning is very wide, but there is a specific method in machine learning, which is called semi-supervised learning, that would aim to perform some classification task with 2 input ingredients. One will be to have data points here, those dots, that are connected in some way. So you have a structure, a graph. But on the other hand, you also have some input information, which is given by the darker nodes here. And those nodes, you already know the class they belong to because it's some input information. For instance, you might imagine a data set in which you have patients that are susceptible for a diagnosis, and some of those patients are already being diagnosed by experts, and you would like to know if others can be diagnosed automatically, just seeing if they share some symptoms. The idea so would be to use diffusion processes to exploit this graph and the input information to say, okay, in this part I have green nodes because I start from this dark red node, and on the other side I have this light blue because I start from the dark blue. So the problem is that, of course, these methods are very impacted by the network structure. For instance, you might have some problems in your graph, some spurious edges, or you might have unbalanced scenarios in which basically you might have more labeled points on one side here and few one here, or you might have more links in one side than the other. And those unbalanced scenarios are very impactful on the result of those methods. So the idea will be to go forward to modify the diffusion processes and try to tackle these 2 issues. So as an example of the impact of such problems, we can take data points here that are shaped in 2 moon fashion. And you cannot see it here, but you have links that connect the two moons here, and also in the middle of the moons. So the expected result would be that here this node is pre-classified as red, and I would like the red to spread all around the moon. And here you have a blue pre-classified node, and through the method, I would like to have all this moon to be classified as blue. So with the standard methods, in this case it is the PageRank method, you actually can see that this blue thing basically invades the other class, the blue color, so the blue classification, and red also here invades this class. Why this? Well, because here you have some links, and also here in the middle you have some links, and those links are the spurious one that made these classes to be invaded. So we would like to fix that, and more specifically, what does this semi-supervised learning method do? You have two terms to minimize. One is graph dependent here, because you have this two form and that contains the Laplacian matrix. We see it here is defined as usual as the degree, diagonal matrix, and the adjacency matrix. And on the other side, you have another term that you would like to minimize, in which you have two ingredients. One is your classification function. It is just a matrix with n rows, because you have n points, and k columns, because you have k classes. And the other y here term are the ground truth labels. So it's a matrix in which I encode the pre-existing information. So what this term does, basically tries to ensure that your classification function, which is the objective, is very similar to your ground truth labels, because on those one, you already had information on the class of the nodes. So the whole problem boils down to minimizing these two terms. As I said, one graph dependent and one label dependent, and the relative strength of the two is governed by this mu parameter. So I can decide that I trust more the graph structure or the input labels. When you minimize this functional, you are able to analytically solve it, and you obtain that your classification function f depends on the y, so the input labels, but also on the inverse of this matrix here, with some parameter alpha here that it is defined from the mu parameter, which was the relative strength of the graph term and input label term. So where does this diffusion come into the picture? Well, it comes because when you look at this classification function, the result of the minimization process, you might recognize that the core of this matrix is given by the transition matrix. The transition matrix of a common random walk. And so basically, when you take a specific method, which is the PageRank, you have that your classification function is the probability distribution for a random walk, but it is a random walk that it has also an extra feature, which is a restart with some probability, and this probability is given by 1 minus alpha, so it's governed by the mu parameter that, as I said, balances between the graph term and the label term in the functional to minimize. So you have that basically the way you classify your node is a result of a specific diffusion process, and this diffusion process is exactly the same one that you perform when you do PageRank. So the problem, or the point that you can improve, is that when you use standard random walks, you just go from one node toward another one that is addition. It is directly connected. So it is exactly where we can do better, because in this case, we plugged Levi-Flight, so these anomalous diffusions that we discussed before, in these semi-supervised learning methods. We used, in this case, the definition given by Diaskos and Mateos in a string of publications starting from 2012 here. And we use the fractional Laplacian, and it is just defined as the eigenvalues here to some power gamma. And you can redo all the calculation and basically take this operator and rederive another classification function that in this case now it is influenced by this gamma parameter, because you have new weights here, W gamma, and you also have new degrees, D gamma, that are defined here in this formula. So how does this classification function behave? And the gamma parameter, actually, it is able to trigger two very different regimes. So the first one would be a regime in which gamma is between 0 and 1. So just to recap, the picture we saw before is a configuration in which these croissant shape data are misclassified. They are misclassified because you have links connecting the two classes here and here. And so you have this invasion of the red here and blue here. But when you have your fractional method, so you use this gamma dependent method, you see that you are able to recover a new classification function, that it is a lot less affected by the links between the two classes. And so you still have some invasion here, some blue dots and some red dots, but overall the result is a lot improved. And the reason why is basically because your diffusion now, it's in some sense more diffusive, is enhanced, and basically those spurious edges here and here aren't any longer impacting so much your classification result as it was the case here. So you can do a little bit of accuracy testing of the method. We see here the average accuracy with respect to the restart probability. So the restart probability, as we saw before, is dependent on the mu parameter, so on the relative strength between the graph term and the label term. So it means that when mu is very big, I trust a lot my input labels, and so I would like my result to be affected by those input labels. So the problem that arises here in high probability regimes is that when this probability is very high, standard methods perform very poor. And we see it here, the page rank and the standard Laplacian methods, which are just two variants of semi-supervised learning, that basically in this regime of high probability, they have a very low accuracy. On the other hand, if we take the fractional version, so here the red curve and the blue curve, so fractional PageRank and fractional standard Laplacian, you have that in this interesting regime, which is again the high probability of restarting, so my labels are very important, both methods perform very well. So they, through the fractional regime of diffusion, we are able to also allow the input label to be very important. So the other impact that this gamma operator creates appears in the interval where gamma is bigger than 1. In this case, heuristically, what this fractional Laplacian does is, I would say, mitigating the immunogenesis. For instance, we can take a situation in which we have an imbalance between the link density. Here, this module it has a little bit more links than than this one. And in those cases, in general, methods are very affected by this case, in particular the standard Laplacian. We see here the blue curve, which is the standard Laplacian method, and the accuracy here on this method is very low. But then if we take this gamma parameter to become bigger than 1 here, the accuracy increases, and so we're able to correct this different link density thanks to this gamma parameter that modifies the way I'm able to, so to speak, play with the structure. On the other hand, and it is quite interesting, the fractional page rank is actually performing better in another gamma regime, which is up to 1.5, and then its accuracy decreases. Another example is when I have an imbalance in information. So I have more input labels here and then here. And again, in this case is very problematic for standard methods, because you would have, in general, that this class ends up eating this class. So you would have all those points classified as blue. But if we have this fractional Laplacian method, we can correct this. And in this case, we see the fractional page rank, and the different curve refer to different imbalance of labels. So 2 to 1 the red, and 5 to 1, and 10 to 1. And the interesting part is that the accuracy can be improved here, those plateau, playing with the gamma parameter. So we are able to cancel out this imbalance of information that we have from one model to the other. The last thing to be noticed here is that when you define Laplacian with fractional power, and you put this gamma parameter bigger than 1, you obtain a new graph with generalized weight W gamma. The point is that those weights can be negative. So when you then try to interpret this classification function as a result of a random walk process, you cannot do it anymore, because addition symmetric negative weight cannot be transposed into a transition probability matrix because of the negativity of the weight. So the interpretation of such result cannot be any longer related to random walks, but is still open to research, because you are now in the realm of signed graphs, so graphs with positive and negative links. So that was my last point. You have all the calculation of what I've been explaining so far, and a few pointers here, the work of on super diffusion and the subdiffusion one, and also the machine learning papers. And on this, I would like to thank you for your attention, and for any question, please write me.